We are from group number 12 from section number 2. Our group consists of Muhammad Alfa Arif bin Adib Mahmudi, Muhammad Shami bin Shafi, and Kashwin Alanki Rameswaran. For our project, we have chosen Smart Water Irrigation System. So Smart Water Irrigation System uses 4 inputs, which is soil moisture sensor, rain sensor, temperature level sensor, and water tank level sensor. And we will name these inputs as A, B, C, and D respectively. And for our outputs, we have 3 outputs, which is irrigation pump, cooling spray system, and alarm. And we will name these 3 outputs as O1, O2, and O3. For our logic system, we have created 2 types of logic circuit. One using basic gates configuration, and another using NAND gates configuration. So for our basic gates, we have used 3 types of gates. First is NOT gate, second AND gate, and third is an OR gate. So for our basic gate configuration, I will now show you how you can simulate this configuration using Quarter software. First, you will need to place 4 inputs, and then after you have placed those 4 inputs, we will rename them as A, B, C, and D based on our inputs. After you've done that, we need to place our logic gates. First, we'll start by placing NOT gates. For NOT gates, we have 3 NOT gates, so we'll place them, and 1 3 input AND gate and 2 2 input AND gate. After you have placed these AND gates, we will now place 1 OR gate. After that, we will place our outputs, which is O1, O2, and O3. So once we have placed all our inputs, logic gates and outputs, we will connect these inputs and logic gates and outputs based on the block diagram that we have sketched earlier. So we will connect them, and then there you have it. We have successfully simulated our basic gate configuration. Now we will move on to our NAND gates configuration. So just as earlier, we also have 4 inputs and 3 outputs. We'll place them, and after we have placed our inputs, we'll rename them just as earlier to A, B, C, and D. So for our NAND gate configuration, we use 10 NAND gates. NAND gates configuration are a special type of configuration because NAND gates have a property of universality, which means you can use NAND gates to almost simulate any types of logic gates. So for example, when you connect one input to a NAND gate, you can invert that input. So we'll use this property to simulate our logic gate. So we'll place those 10 logic gates, 10 NAND gates, and we'll connect them to our outputs. And then we will connect these inputs, logic gates, and outputs according to the sketches. After we have simulated both our logic configurations, we can also create a timing diagram to verify our outputs. And we can also do this in Quartus software. So creating a timing diagram for logic gates in Quartus 2 is typically done through the simulation process using the vector waveform file, VWF. This VWF allows you to define the input signals over time and then visualize the resulting output signals, creating the diagram. First, you need to create your logic gate, logic circuit, as we have done earlier. After you've done that, we need to set up the simulation. After our circuit is compiled, we will need to create a VWF for simulation. So create a new file, go to file, new, select verification, debugging files, and then choose your name or your file name, and then set end time. In the VWF window, set the desired length of your simulation. After you've done that, we need to add nodes. So we need to add the inputs and output signals of our design to the VWF window. So we insert node or bus, double click on the name column or go to edit, insert node or bus. After you find the nodes, we need to select the inputs. Once you have done that, we need to define input waveforms. So select a signal, use the toolbar to insert 1 high or 0 low, and use the clock tool as well. And after we have done all this, we can run the simulation by saving the VWF file and running the functional simulation button, the blue icon. Once you have started the simulation, we can view the results. So this is the waveforms of the both configurations that we have designed, and from this two figures we can see that the output waveform for the NAND gate and the basic gate matches exactly. So this confirms that the logic circuit that we have designed is successfully implemented and is correct. So the timing waveform illustrates how digital signals such as inputs and outputs change over time. It visually represents transitions between logic levels 0 and 1 in response to clock pulses or other conditions within the system. Timing waveforms are essential for analyzing the behavior of logic circuits as they help verify functionality, observe signal responses, and ensure that the circuit performs as intended. Thank you very much. This is from Group 12 from section number 2.